So welcome to all. Myself, Dr. Santhosh Singh, working as an associate professor in Department of Physics, Institute of Aeronautical Engineering. Today I am going to discuss about semiconductor heterostructure and lattice matched layers. Okay, so let's start the topic. So what is the heterostructure or semiconductor heterostructure? So to know the semiconductor heterostructure, there are some prerequisite things. Means you have to know about ternary semiconductor or quaternary semiconductor, and these are also known as alloy semiconductor. Okay, so how these semiconductor are different from the doped semiconductor, and what is doped semiconductor? You have to know all these things. So I will try to give some basics things about all these things. So what is doped semiconductor? So doped semiconductor is nothing but once you add the impurity in fourth group element, third group element has a impurity you have to add in fourth group element, then you will get a kind of p-type semiconductor. Once you are adding the fifth group element as a impurity with fourth group element, you will get a kind of n-type semiconductor. P-type, n-type. So fourth group element, and if you are adding third one with fourth, you are getting p-type. If you are adding fifth group element with fourth, you are getting n-type. So these are doped semiconductor. You are doping something with fourth group element. For example, suppose you are one to n-type semiconductor, and you have a fourth group semiconductor like germanium or silicon, and once you add in these germanium or silicon with arsenic or antimony, maybe you will get a kind of n-type semiconductor. Why there will be one additional electron will be free there. They are not making any covalent bonds with their adjacent atom. So that electrons will act as a free charge carrier, and you will get a kind of n-type semiconductor where majority charge carriers are electrons, these free electrons. Okay, and once you want to get a p-type semiconductor, you can add some aluminum or gallium in silicon, okay, or germanium. Okay, so you will get a p-type semiconductor, aluminum. Okay, so basic fundamental things, the fourth group element which are naturally found as a semiconducting material, and these semiconductor material are known as intrinsic semiconductor. And once you add or doped some third group element or fifth group element, so after doping, whatever the compound you get, that semiconductor, either it will be fifth group, either it will be n-type or p-type, depends on your doping element. So that whole thing after the doping is known as doped semiconductor. So basically that is binary semiconductor, either gallium arsenide, or if you are adding some third group element with fourth group element, so you will get some n-type semiconductor. So I will tell here. So p-type silicon, what I told. So what is doped semiconductor? So p-type silicon. Suppose you want to make a p-type silicon, then silicon is doped by boron. See, boron is where? This is boron. Okay, and this is third group element, and this is silicon, fourth group element. So once the boron is doped with silicon, so that silicon, there is no such type of name, that impurity, that boron is act as an impurity, and that silica is entire silica. It's after doping, their name is itself a silica. Okay, so you will get a P-type silicon. Okay, if you want to make N-type, then you have to dope with arsenic or normally phosphorus. So see here, in silica you will dope arsenic. This one is arsenic, and this is phosphorus. So once you dope these materials or these elements with silica, the silica atoms will behave like a silicon material will behave like a N-type semiconductor. Okay. So what is the point that we see that for doping you dope the material that you add an impurity which is from the adjacent group. Okay. So if you want to make N-type or P-type semiconductor or doped semiconductor, you are doped with adjacent group material. Okay. This is group 4 semiconductor, and if you add an impurity from group 3rd, it becomes P-type semiconductor, and if you add an impurity from group 5, it becomes N-type semiconductor. So that is the basic fundamental thing about doped semiconductor or normal semiconductor. Now what is the alloy semiconductor? Alloy means ternary or quaternary semiconductor. So actually, suppose gallium arsenide. Okay, where is gallium? See, this is the gallium, this is the arsenide. So once you make these gallium, once you dope something, or if you try to make some combination of 3rd and 5th group element, gallium arsenide or gallium phosphide, these type of material will also behave like a semiconductor, but it is not in the normal form gallium arsenide. You can't say it is a alloy or ternary or quaternary semiconductor, but once you doped again in gallium arsenide, you got some semiconducting property in gallium arsenide, and once you replace these gallium by, let's suppose, in some fraction by boron or aluminum or indium, gallium, indium phosphide, indium, suppose what I am telling, gallium arsenide. Now in gallium is 3rd group element, and now you are replacing the gallium in some fraction by same group element by indium or aluminum or boron. So let's suppose I am replacing that gallium with the indium in some fraction. So gallium 1 minus X, indium X, arsenide. Okay. Now gallium is replaced by same group element. Okay. So such type of things is alloy semiconductor. And here see 1, 2 and 3. 3 elements are present there. So you can say these are ternary semiconductor. Ternary semiconductor. Okay. So why I am talking about these ternary or quaternary semiconductors? Because these semiconductors are very, very important for device application or device fabrication. Doped semiconductor, like you doped silicon with phosphorus or arsenic or boron for getting P-type or N-type. So that semiconductors are useful for you, but useful in electronic application. But our aim or our concern is for optoelectronic application. And optoelectronic devices are little bit bigger in size comparison to electronic devices. Okay. So you have to make some layered structure. Basically, how to make a doped semiconductor. Let's suppose some silicon, having some length in micron and breadth in micron, and put here some phosphorus or arsenic. So these entire silicon are normally maybe N type. For the case, what will be the nature? I can't predict. Or sometimes silicon are found as a P type, sometimes silicon is found as N type. Let's suppose it is N type, and you put over here arsenic in a small amount. What happened? And give some temperature. What happened? These arsenic try to diffuse inside the silicon. So in very small region, this silica convert as a N plus type. Okay. Now nearby, put here some boron or aluminum. This boron or aluminum will also try to diffuse inside the silica. So nearby the small region will convert as a P plus. Okay. Now these regions are behave like a P and N region, and you can get a kind of diode. Okay. So you can construct either diode or transistor or some electronic devices over a very small region. Okay. But for optoelectronic devices, some larger scale dimensions are required. Okay. So for that purpose, the ternary or quaternary semiconductors will be used. Okay. And how how to make these ternary and quaternary semiconductor? To make optoelectronic devices, you have to grow these ternary or quaternary semiconductor, deposit these ternary or quaternary semiconductor as a layer by layer. Okay. So you can say that is the epitaxial growth. First you have to take any substrate. Okay. Take any substrate. And that substrate also made with some semiconducting material like silicon or gallium arsenide. Now make some layer of gallium phosphide or gallium indium arsenide over this gallium arsenide layer. Make some second layer over this gallium indium arsenide. Let's suppose gallium aluminum arsenide. Okay. So such type of growth. Let's suppose this gallium or aluminum arsenide is acting as a P type. This gallium indium arsenide is maybe acting as a N type for the case. For example, so this junction is behaving like a PN junction, and these two layers are made with different kind of material. This first layer is for gallium aluminum arsenide. The second layer is gallium indium arsenide. Okay, and these materials are also have some different band gap value, e.g. Now, if these materials, gallium aluminum arsenide and gallium indium arsenide, perfectly lattice, their lattice are perfectly matched, then this junction is known as heterojunction. Obviously, this is the PN junction. So you can say that this is the hetero-PN junction. Why? Because two different types of materials are used to make the PN junction, and their band gaps are also very, very different to each other. Okay. So that epitaxial growth of semiconducting layer, different type of semiconducting layer, either P type or N type, over the substrate will make a kind of heterostructure, and that heterostructures are very, very important for optoelectronic application. Optoelectronic, not electronic. In electronic case, doped semiconductors are maybe enough. But for optoelectronic device application, their dimension, that device dimension is little bit large. So you have to construct the layered structures of semiconductor, and these layer structures will be known as heterostructure heterostructure PN junction or heterostructure junction, when these layers are formed with different kind of material and their band gaps are also different. That is the fundamental concept of heterostructure, and that will be used for optoelectronic device application. So all these things are written here. Alloy semiconductor, or what is alloying? So it is from the same group. Same group means you have to suppose gallium arsenide. So you have to replace this gallium or arsenide with same group element. Suppose you want to replace in some fraction, not all, or you can replace this gallium in totality, but again it will become a binary. So you want ternary or quaternary semiconductor. So if you replace this gallium in some fraction by aluminum or indium in same group element, it will come as a alloy. It was from the same group. That's why it is mentioned here. For example, aluminum gallium arsenide, X fraction of gallium is replaced by aluminum from the same group. So the first difference is the substitutional element here in alloying is from the same group. Means what is the difference between doped semiconductor and alloy semiconductor? So there, in doped semiconductor, there is no such type of criteria. Either you can choose third group element or fourth group element. But in alloying, suppose first you have to take some binary semiconductor, then you have to replace any element by same group element in some fraction. So that is the first difference. It was from the same group, and substitutional element here in alloying is from same group. And why we want to do all these things? To change or enhance the conductivity, or for band gap modification. That is very, very important for optoelectronic application. And what are the heterostructures? So heterostructures where you grow the semiconductor of different type with different band gap on substrate. Just now I told. So if you look at the fabrication of device in electronic devices and optoelectronic devices, in general, optoelectronic devices are much bigger in size compared to electronic devices. You know that in integrated circuit with very large scale integration on a small chip, you can have a million electronic components on a single chip. But usually in electronics, in a very small region, you can construct a million of electronic devices like diode, transistor, capacitor, like that. Not capacitor, diode, transistor, or any other electronic devices. But usually in optoelectronic devices such as laser diode or photodetector, there are much larger in size. So, and typically in optoelectronic chip are what are the called photonic integrated circuit, PIC, photonic integrated circuit, PIC. That is IC, integrated circuit. In electronics devices used IC, but in optoelectronic devices, that chip is known as photonic integrated circuit, PIC. So optoelectronic integrated circuits are photonic integrated circuit. The number of components on the chips are generally very few. In electronic circuits, IC, you can integrate a million of electronic compound. But in PIC, photonic integrated circuit, the number of components on the chips are generally very few, up to 3 to 8, a small number, because each component, the dimensions are typically 10 to hundreds of micron, means like 20 micron, 18 micron to 100 micron. Whereas in microelectronics, we have a component which go to the sub-micron region. Okay, so the dimension are extremely small, or the size of optoelectronic component are very large. So in electronic IC devices, the electronic component size are very small, but in the optoelectronic devices, the size are little bit large compared to electronic devices. When the chip comes, it passes through. Once the chip is prepared, there are several tests will happen to know the performance of that optoelectronics devices or photo integrated chips. Okay, so when the chips comes, it passes through the several stages, several process of diffusion and deposition happen. So these layers are the layers which are deposited on the top, are called epitaxial layer. Grow layer by layer on the substrate. Basically, there are two processes. One is diffusion and other is epitaxy growth on the top. And most of the electronic chips use both these processes. And finally, you come with a very large number of devices. So most of the optoelectronic devices are fabricated by epitaxy, which means you start with substrate. Let's suppose this is your substrate, and then deposit layer by layer. Okay. So this is a kind of epitaxial growth. And this is the substrate. This substrate also has some property, either it is also a kind of semiconducting material. And these layers are epitaxial layer. And if these layers are with different kind of material with different band gap, these junctions are known as heterojunction. Okay. So for optoelectronic devices, these heterostructure or heterojunctions will play a very important role. We will discuss a certain devices structure at a later stage, but you deposit a different layers, p dope layer, n dope layer, and so on. You deposit a layer structure. So the growth is known as epitaxial growth. It is epitaxial layer. There are three commonly used process for epitaxy. How you can grow the epitaxial layer over the substrate. So there are some process, namely liquid phase epitaxy, LPE, vapor phase epitaxy, and here in vapor phase, chemical vapor depositions will come, and MBE, molecular beam epitaxy. Okay, so we will not go into the discussion of how to grow the fabrication here, because I mentioned it would be different course. Okay, so actually how to deposit the layer, that is the different thing. That means out of our course we are dealing with optoelectronic, semiconductor optoelectronic devices. But once the layer is grow, what is the quality of layer? What is the, if the layer is grow by somehow in some manner, what the name should be that layer? All these things we should know. Okay. So these are some process: liquid phase epitaxy, vapor phase epitaxy, and molecular beam epitaxy, where you will deposit the molecules in the form of layer. Molecular, it is very costly experiment, molecular beam epitaxy. Okay, so once you will deposit with the help of molecular beam epitaxy, the layers will matched with each other, means that lattice will match. Mismatch lattice and match lattice. There are two concepts. I already told what is heterostructure. So again I am telling, let's suppose this is the substrate. This is a kind of epitaxial layer. This is first layer. Now you are growing second layer. Okay. Second layer, first layer, substrate. Now first layer is formed with let's suppose a kind of X material, and the second layer is formed with a kind of Y material. Both materials should be different. Then only the heterostructure. You can say these are heterostructure junction. And band gap of these X and Y, EGY and EGX should also be different. Okay. Then only you can say this is the heterostructure. Now, let's suppose these are the atoms involved in X material, and these are the atoms involved in Y material. Let's suppose this is the X atom, and let's suppose this is the Y atom. Now these X atom will, if these X atoms, the bottom layer of X atom will form the bond with Y atom, means the lattice is perfectly matched. So you can add some additional term, heterostructure matched layer. That is our topic here. Okay. So heterostructure matched layer. Heterostructure are there, but layers are matched. And let's suppose this is X, this is Y. Now Y and Y is like that. So one atom is formed the bond with this atom, and this atom will try to make a bond like that. This atom will also confuse. It will make a bond with this atom or this atom. Okay. So let's suppose the bonding formation is like that, and this atom don't found any atom to make a bond. So a kind of dangling bonds is there, where there will be no atoms present to make a bonding formation. Okay. So these are some kind of mismatch of layer, and that mismatch layer is known as lattice mismatch. So heterostructure matched layer and heterostructure mismatched layer. There are two concepts. So matched layer is okay. Once the heterostructure matched layer means there will be no non-radiative state in between conduction band and valence band. Why? Because these dangling bond will create a non-radiative state in between the conduction band and valence band, and these non-mismatched layer are these dangling bonds is also very important for some particular device application. Okay, because if you want a non-radiative transition occurs due to some involvement of phonons, means you don't want any kind of emission in form of photon. So some mismatched layers should be there. But if you want a perfectly radiative transition, means in the term of photon some transition will happen, then definitely it should be the heterostructure matched layer. Okay. So these are some things about semiconductor heterostructure match layer. Thank you. And in my next video topic, I will try to cover some particular heterostructure match layer. Thank you. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.